Greetings, Physics 2001, Section 102 students. That's the afternoon section. This is lecture 19, the one that would normally have happened in the afternoon of Tuesday, March 31st. So first, let me start out with some general organizational notes like usual. The course webpage, please see that for copies of the slides. The slides are, of course, also on Lon Kappa. What you get on the course webpage is additionally video links and links to the Google Docs Q&A associated with the given lecture. So if you have a question about the lecture or even about the class, email me the question. I will post that and the answer. It will be anonymized, so don't worry about your name's not going to be there. And you can find that on the course webpage. So this particular lecture is going to be on simple harmonic motion, and it's the first of two of these. So there's going to be two on simple harmonic motion, and really today we're mostly just covering a spring force in preparation for describing how springs oscillate and undergo oscillatory motion, which the simplest form is the one called simple harmonic motion, and that's what we'll do. Before we do that, keep in mind that you have a homework due Friday. Your lab is also due by noon on Friday, and we're still going to have the pre-class assignments due. An email will go out, and likely you will already have received it by the time you hear this. An email is going to go out with the Microsoft Teams links to the different TAs' help room sessions, and you have already received a Teams link for the SI session. So Emma Chubb has sent this out. She will host live Microsoft Teams sessions that you can participate in to mimic what is done with SI. What the TAs are going to do is they will also have a live help room, 6 to 9 p.m. Wednesday and Thursday. Note that there is a single TA on Wednesday and there are two on Thursday. An email has already gone out with their contact information. On Thursday, please just flip a coin to pick which one you're going to email, because that'll help balance out their workload. One thing that the TAs will also do for the virtual help room is I realize not everyone's going to be able to make it to the 6 to 9 p.m. time block on those 2 days. So what you can do is email a question to the TA, and as long as you get it to them before the 6 to 9 p.m. window, they will do their best to answer your question via email as soon as is practical. Of course, please do not wait until 8:55 p.m. to email them something on Thursday. If you do that, I wouldn't blame them if they take a while to get back to you. For office hours, I'm just going to do those via email. I don't think personally, it's not too practical for me to do office hours at the time I was doing them right now, just because basically running our home daycare. So please just send me an email and I will give you a detailed answer. And if it's related to one of the lectures, I will also post the answer in one of the Google Docs question and answer sheets. Okay, the next big organizational thing is midterm 2. So originally this class was going to have 2 midterms and a final. We're now going to have 3 midterms and a final. So midterm 2 is going to cover a little bit less content. It's going to be through circular motion, so the things we covered before spring break. The exam itself is going to be open and available for you to take from noon on Monday, April 6th through 6 p.m. on Tuesday, April 7th. However, note that's the open window. Once you start it, you'll only have 90 minutes to complete it, so it's a timed exam. And we've written it so that it's roughly half the length of a usual exam, so hopefully this should work. We're basically budgeting an extra 30 minutes for you to fiddle with the Lon Kappa stuff. Note that after 8 p.m. on Monday and through 6 p.m. on Tuesday, there's expected to be less traffic on Lon Kappa based on what the other classes are doing with their exams. So it might be good if you can to take the exam in this time window, but it will be open from noon on Monday, April 6th. But later just might be a better idea. Okay. So if you have a problem, let's say your internet fizzles out mid-exam, please contact me or Dr. Picard as soon as possible. I realize if your internet's totally dead, that's not going to be very soon, but try to do it as soon as you can, and we will work on an accommodation. Lon Kappa maybe cool enough or creepily enough, pretty much records everything that you do. So we can see when you started, how long you worked on it, what you were working on, and basically then we will be able to calculate how much time you have left. So we can figure out some accommodation for you. On a related note, if your life circumstances wind up affecting your ability to complete any of the class's assignments, please let me know. I do want to be flexible here because I realize that everyone's under some additional strain. One more important organizational thing is that these slides are, of course, recorded in advance. I try to do that so that you have extra time to get a chance to look at them. But that means that some of these details can change, right? So please keep an eye on your email, and that's always going to supersede what I say here. What I say here, I try to be as correct as possible, but things, of course, change. For the exam, please set aside some time to study, okay? As I've said before, I think it takes about 8 hours of studying if you want to get an A on an exam. And, you know, hopefully that's not too terrible. You know, if you set aside between now and the exam time, you know, an hour or two each day, then you'll easily reach that. So for that, I really recommend practicing problems without looking at the solutions. I think for physics, that is the best way to study. Okay, so let's move on to the content. So this in the next lecture are simple harmonic motion. So the kinds of questions that we want to be able to answer is if we want to have a clock and we want it to tick once per second, how long do we need to make the pendulum? So it turns out that this pendulum length will directly control how long it takes to undergo one oscillation. So you could design a grandfather clock, for instance. Again, predicting the motion of pendulums, which can be interesting or can be practical, you need simple harmonic motion to do that. If you want to understand different types of oscillatory motion, just in life, simple harmonic motion is usually where you start. And today we're going to start with springs because that's one of the more common oscillators, that and pendulums. And for instance, we'll learn about the spring constant, and you can basically compare the difference between a race car suspension, which is a very stiff spring, large spring constant, versus a more comfortable ride like you might have on a Cadillac. Okay, so we'll start out with a practice question. Again, you can review these on Top Hat. So the first question is, what are the units for the spring constant? Take a moment, think about it. I'm going to assume you've paused and you've come back. And you know from your reading that the units for the spring constant must be newtons per meter. That's because the spring force is equal to K times X. The spring force is equal to the spring constant times the displacement. So therefore, the spring constant is equal to the force divided by that displacement. Force in SI units is the Newton, and displacements in SI units is the meter, so that's going to be newtons per meter. Okay, so for springs, that equation that I just mentioned, which you likely now know already from your reading, is known as Hooke's law. So in words, the law is that the displacement of a stretchy object, so like a spring, from its equilibrium position, which is where it would be if you weren't messing with it, this requires a force that is linearly proportional to an intrinsic property of the spring, which we refer to as the spring constant K. So K roughly tells you how stiff is this spring, how resistant is it to stretching or compressing. So the way we write this is that the applied force is equal to the spring constant K times the displacement. And you can see pictorially here what we mean by the displacement. Let's say we have a regular spring just hanging out, and we stretch it. The difference between where the end of the spring started and where it finishes after you've stretched it, that is this X, that is the displacement. Okay, so that's for the applied force. And again, the spring constant is in newtons per meter. Now this is known as Hooke's law. I guess it used to be easier to get a law named after you, so good. good for him. Now keep in mind that the sign of the displacement depends on the direction of the displacement. So this is like usual, you need to define it, what the positive direction is. So for instance, I could say that the positive x direction is to the right, and then this would be a positive displacement in the upper scenario here, and the bottom would be a negative displacement. Similarly, as long as I define the position increasing, the positive x increasing to the right, then the upper scenario, this is a positive applied force. The lower one, this is a negative applied force. Okay, so pay attention to the direction. Now, with springs, there's an applied force and there's a restoring force. Okay, so the applied force, for instance, this is the one that we apply, right, as the name says. The restoring force is the spring force. So this is the spring trying to get back to its original unstretched or uncompressed position. So for instance, if I pull, then the spring force rather is going to oppose. It's going to be equal in magnitude and opposite in direction to the applied force. So what that means is that the applied force, right, that was equal to k times x, spring constant times displacement. The minus the spring force is going to be equal to k times x. Okay, or more commonly, the way we write it is the spring force is equal to minus spring constant times displacement. Okay, so the reason these are useful to know is sometimes you might be told the spring force, sometimes you might be told an applied force. Of course, you can work between one and the other, but just pay attention which force it is that you're working with. So a spring, keep in mind, don't be too rigid in your mind about what a spring is, okay? We're really talking about anything that stretches or compresses and then tries to return into equilibrium. So it applies to anything at all with any elasticity. If you want to sound fancy, that's what you'd refer to it as. So the elasticity is really just stretchiness. So for instance, this works for a rubber band, it works for a guitar string, it can work even for an object like concrete and rebar, right? That does have some stretchiness to it, for better or for worse. So also really interestingly is that if you have a really complicated solid, like we're talking about a relatively microscopic object here that's held together by molecular bonds, you can represent this by a system of coupled spring systems. So this is actually still used for practical research today. So for instance, when you're talking about the extracellular matrix that supports cells, this is often modeled as, rather than having a bunch of molecules that are connected by molecular bonds, you basically treat each molecule as a node and the bonds between them as a spring, and you can model how this thing is physically going to behave based on this spring system, which is kind of amazing. Also, for instance, if you take a chromosome from a newt and you plot the force that is applied to this poor newt chromosome versus the extension here. So for instance, how much force did it take to extend the newt chromosome from here to there to there to there, and you're looking at the tweezers kind of that are pulling on it. You see that applied force is linearly related to the extension, just like you'd expect from Hooke's law. So this is actually quite practical, and it extends far beyond just a simple spring system. So let's do a practical question here, just a qualitative one. So what we have here is a graph of the force versus the displacement, and you have three different springs, 1, 2, and 3. And the question is, which one is the stiffest? So which one has the largest spring constant? Just take a moment, think about it. I'm going to assume that you've paused and come back. And you see that 3 must be the one with the stiffest spring. This is the largest spring constant. So why is that? Stiffness indicates how large our spring constant is. So stiff means a large spring constant. And the applied force is equal to the spring constant times the displacement. So then our spring constant is the force divided by that displacement. And so what that means basically is we can calculate what's the delta F that you get for a given delta displacement. So for a given change in applied force, what's the change in displacement? And so this basically is a rise divided by a run, right? That's a slope. And so a greater spring constant is a greater slope in this force versus displacement graph. Okay, so let's do a follow-up question here. Again, qualitative, but a slightly different scenario. So let's suppose that you attach a mass to 3 identical springs and you stretch them by 1 centimeter. Okay, if you attach that same mass to one spring and displace it by 1 centimeter, how much force would the single spring system require in comparison? Okay, so these gray boxes here, these are the same mass. In this case, I've attached it to 3 springs in parallel that have the same spring constant, and I'm applying some force to basically stretch this thing. And in this case, I have the same mass on one spring with the same spring constant. So how much force would the single spring system require in comparison? Let's take a moment, think about it. We'll assume that you have come back after pausing the video, and you see that naturally it's going to take less applied force for the one spring system as opposed to the 3 spring system. So why is that, right? Remember, the spring constant is the applied force divided by the displacement, and this is going to apply to each of our 3 springs. Okay, these are being stretched in parallel, so you're stretching one next to the other next to the other, so that's called in parallel. And so the spring force applies to each of these. So therefore, it's going to take 3 times the force to stretch all 3 springs at once than it does to stretch one. And the reason I'm stressing in parallel here is you could imagine having one spring connected to another lengthwise, connected to another lengthwise. That would be called in series. And in that case, you basically just have one long spring with the same spring constant. And so that would be the same as a shorter spring with the same spring constant, right? So it matters that we're talking about in parallel here. So one thing that we can do with springs is we can measure the spring constant using a mass. So we take advantage of the fact that we all remember that the gravitational force is equal to the mass times little g around the surface of the Earth. So this little g is our friend, that 9.8 meters per second squared. So we know the force of gravity, and then therefore if we attach a mass to a spring that's going to stretch the spring, we can measure the displacement, and as long as the system is in equilibrium, then the spring force, or rather the applied force, is equal to the gravitational force, right? So kx is going to be equal to mg, and we can therefore solve for the spring constant. So basically we have a mass, a known mass. We know the force of gravity is mg. That's going to be equal to the applied force, which is equal to kx. And so then we can go ahead and solve for the spring constant if we've measured displacement and we have measured the mass of the object, and of course we know little g. So then the spring constant is just going to be the mass of that, in this case, blue object hanging from the spring, times little g divided by the displacement. And remember, the displacement is take the end of the spring where it was when nothing was acting on it, when it was just sitting there chilling, and you added a mass to it, and now it has stretched, and the end of the spring is at some distance x away. That is the displacement x that goes into this equation here. So let's do a quantitative question here. So let's say we have a 0.2 kilogram mass. It's hanging from a spring, and the displacement of that spring, how much it stretches, is 0.1 meters from the equilibrium position. So the question is, what is the spring constant of this spring? Let's take a moment and work it out. I will assume that you have paused the video and come back, and you will have figured out it's 19.6 newtons per meter must be the spring constant, which is what it is. So again, the applied force here is equal to the spring constant times displacement. That's equal to mg in this case because we're just hanging a mass vertically from a spring. And we solve for the spring constant, and then we can go ahead and plug in the numbers that were given in the question, and we arrive at our spring constant. Okay, so let's do one last semi-quantitative question for springs before we move on to the exam review. And you might wonder, wait, really? I thought this was a simple harmonic motion lecture. Well, this is just to get all of the spring knowledge out of the way so that next lecture we can handle all of the oscillation stuff. Okay, so on to the question. So we have different systems here. We'd have different springs. So we have spring A, B, C, and D. They are all first shown in their unstretched position. So for instance, this is spring A in its unstretched position, B unstretched, C unstretched, D unstretched. And then we stretch them by some hanging mass. So in A, we hang this guy and it stretches this much. B, we've now hung this mass and it's stretched a bit more. C, again, different mass, and we can see how much it's stretched. And same with D, we've added a mass to the spring and see how much it's stretched. Okay, so you can use the grid to determine what the displacement was, and the mass is stated, the relative mass is stated in each of these boxes. So what you need to do now is to rank the spring constants. So you know the mass that was applied to the spring, and you know the displacement that resulted, so you can figure out the relative spring constant for each of these. So take a moment and think about it. I will assume that you have paused the video and you have come back. And you'll see that D is the answer. So the spring constants for systems are springs A and D. These are equal, whereas they are greater than the spring constant for B, which is equal to the spring constant for C. Okay, so what we need to do is our equation that only applies for when I have a spring oriented vertically and a mass hanging from it. In that case, the applied force is equal to the gravitational force. And so we can then solve for the spring constant based on the displacement and based on the mass applied. So the spring constant, again, is the mass times little g divided by x. And so if we have the same amount of mass applied, hooked on the end of a spring, but a larger displacement, that means there must have been a smaller spring constant, because that spring constant is the stiffness, the resistance to being stretched or compressed. So if we have a larger displacement for the same amount of mass, that must be a smaller spring constant. Then if we have an equal displacement, but a larger amount of mass, then that spring constant must have been larger. So if I, for instance, I apply 2 times the mass to a spring, and I stretch 2 boxes, as opposed to this system, which has just 1 mass, right? 1 mass unit, not 2. It still stretches 2 boxes. So therefore, the spring constant of B must be weaker than D, right? Because D, you had to apply twice the mass to get the same stretch. So then, taking this step at a time, spring A, it stretches less than spring B for the same amount of applied mass, so it must have a larger spring constant than B. Spring D stretches less than spring C for the same amount of applied mass, so we know that spring constant for D must be greater than spring C. And then finally what we have to look at is, let's look at that applied mass divided by the displacement. And you see that for A, that is the same as for D. So here we've applied 1 mass unit and stretched 1 box. So that m over x is 1 in this scenario. Here we've applied twice the mass and stretched twice the amount of distance. So in this example, we have 2m divided by 2 boxes. And so then the 2's cancel and we again get m over x. So then we know that the spring constant for A equals D. We know that A is greater than B. And then finally, we can also look at the mass over the displacement for B and C, and we see that they're equal. and then you result in answer to this question. Okay, so now this is just a brief review for the midterm that is upcoming on Monday, April 6th through Tuesday, April 7th. Again, you will only have 90 minutes to complete it, but it will be open from noon on Monday, April 6th through 6 p.m. on Tuesday, April 7th. Once you start it, you have 90 minutes to complete it. It will cover content through circular motion, and it will, of course, focus on the things that have been covered since midterm 1. What's following is basically just kind of a brief reminder of the content. This is not intended to substitute anything we covered in the lectures, and it doesn't cover anything new. I just want to remind you of what you need to go and study. Tips for studying. I really think the best way to do this, and I have a lot of experience studying and taking physics exams now, I think, review your notes, remind yourself of the things that you've learned. Maybe go ahead and create your equation sheet. You're still going to want to create an equation sheet for this online exam. Even though it's essentially open notes, 90 minutes is not a lot of time. You want to have your key equations handy and ready to go for you. So review the notes, maybe create your equation sheet, leaving some blank space so that you can add to it, of course. Then try some practice problems per topic. So for instance, go to Top Hat and pick a couple of questions from each lecture and try them without looking at the answer, okay? Try to solve that, and then if things didn't work out very well, then go back to the relevant section in the notes. Maybe read that part of the book in OpenStax, maybe try an OpenStax problem where you also see the solution, and then go back and try a couple more problems from the lecture in that topic. Once you've done that for the lectures that are pertinent for this exam, then I suggest that you go ahead and take the practice exam and see how did you do, okay? Normally, I suggest that you time yourself and grade yourself for kind of an honest assessment. In this case, the practice exam is going to allow you to mimic the real exam to get the mechanics of an exam in log kappa, and so that isn't as pertinent here. We'll kind of enforce that similarity to the real testing environment. So the first topic that we covered following the stuff that was covered on midterm 1 was torque. So remember that the torque, this is a perpendicular component of force applied to a lever arm some distance from the axis of rotation on that lever arm. Okay, so we're not concerned with the total force, we want the amount of force that is oriented perpendicularly to that lever arm. And if you'd like, you can think of this as a perpendicular distance. Going from one to the other is just a matter of trigonometry. I really prefer this method, but in any case, you need to review torque. So the simplest case that you can have is where all of the force is perpendicular to a lever arm, and that's applied some distance from the axis of rotation. So remember, torque is always relative to some axis of rotation. So for this same scenario here, if I were to move the axis of rotation to the center of the board, that means that force would be applying less of a torque because there's less of a distance. So if you want a problem to solve to say, have I mastered torque or have I not? My personal favorite is the series of questions related to having a hanging board with some mass, and you have a cable at an angle that is supporting that board, or maybe it's called a lamp post, whatever it is, and you need to figure out the tension in the cable, you need to figure out the force of the wall on the hinge, and all of that good stuff. So this would be a very good problem for you to master, and if you know how to solve this type of problem, then you're good to go. Now, please do not memorize just specifically this problem. Use this as a way to learn the problem-solving steps for torque. So remember, we basically choose or are given axis of rotation. We then solve for the individual torques that are involved. The sum of the torques is going to be equal to 0 in static equilibrium. So if the object's not rotating or accelerating in any way. And then once those are equated, you can basically then do algebra to go ahead and solve for the force that is relevant. So do not memorize just this problem. Use this as a good example of one that makes you use all the problem-solving steps for working through a torque problem. So the next topic we covered is energy, and that includes work. So remember, good things for the equation sheet. Kinetic energy for a single object is 1/2 times its mass times its velocity squared. The potential energy for that object is its mass times little g, that's 9.8 meters per second squared, times h, where h is the height relative to some reference height. So some height needs to be defined as 0, or you define it yourself, and then an object's height relative to that vertical position will give you the potential energy. Then we also have the work. So work, when we have an applied force, right, that's equal to the force times the distance times the cosine of theta. And what we mean by that is we only care about the force that is oriented along the displacement. So in this example here, you see the person's pushing down on the lawnmower with some force, but we only care about the amount of force that is directed along the displacement. If the force were opposed, or was opposing the displacement, so let's say the lawnmower was moving this way, it's self-propelled, and someone's pushing in the opposite direction, then that would be negative work, right? Because there's 180 degrees between the displacement and the force that was applied in that hypothetical scenario. In the one that's pictured, the force is along the same distance, and so then positive work is being done. Work can also be solved from changes in kinetic energy. So the final kinetic energy minus the initial is net work, or the initial potential energy minus the final potential energy, that is net work. The sort of master equation for energy conservation is that the final kinetic energy plus the final potential energy, that is equal to the initial kinetic energy plus the initial potential energy plus any work done by non-conserving forces. So for instance, if you add an engine into the scenario, that's going to pump extra energy into your system, and so you're going to wind up with more energy than you started. If instead your non-conserving force is something like friction, that's, for our purposes, removing energy from the system, then this will be negative, and you'll wind up with less total mechanical energy than you started with. So if you want one problem to practice, kind of a difficult problem to focus on, to learn all the kind of problem-solving steps, or to apply all the problem-solving steps for energy conservation, I think that this is a good one to try to master. So we have a stunt person starting at some height, right, with some amount of energy. They're all potential energy. They fall some distance, some vertical height, and a pad then opposes their motion as they fall here. They're again all potential energy, but you basically have some initial energy in your system, some final. There was work done by a non-conserving force, and you need to practice picking some reference height, right? Keeping in mind that potential energy is relative to a reference height. And if you'd like, some people like to solve this in terms of an accounting problem. We talked about how energy conservation is kind of like accounting. And so you start out with some amount of money. Some of that money might be removed from the system, and you wind up with less amount of money. And you can use a table to help you solve that type of problem. Another classic one is, remember that the energy and the kinematics are related, right? So you can, for instance, figure out the speed. You take some object, you hold it at some initial height, it's all potential energy, you drop it, and it's just about to hit the ground. If we define this as height 0, then it's all kinetic energy. You can use energy conservation to figure out the velocity of this object just before it hits the ground without using any of the free fall equations. Okay, so remember, this is the kind of thing you can do as well. The next topic we covered is momentum. So the momentum is the mass of an object times its velocity. Velocity is a vector. This is a scalar here, mass, so therefore the momentum is a vector. Keep in mind the momentum is conserved, and it's conserved as a vector. So the sum of horizontal components of momentum of any number of objects involved in a collision, that's going to be equal to the sum of the horizontal components of the momentum of those objects after the collision. And separately, the vertical component of the momenta are conserved. Okay, and when we talk about collisions, we can classify them different ways. So let's say our two objects collide and stick together. That's known as completely inelastic. When they stick together and they're not crushed, or sorry, they don't stick together, they're not crushed or bent, they just bounce right off each other like pool balls or billiard balls, then that is elastic. And why we care is that when they're stuck together, lots of kinetic energy is lost, so kinetic energy is not conserved. If it's an elastic collision, so they bounce right off each other, then kinetic energy is conserved, and that might be useful. Another thing to keep in mind here is the impulse. So when we apply some amount of force over some amount of time, that tells you what the change in momentum for that object is going to be. And we define that as the capital letter J. So an example of a momentum conservation problem for you to solve is these two rail cars colliding. Okay, they collide and they're going to stick together. So your initial system, you have, let's define the moving to the right as positive. In the initial system, the left car has a positive velocity and therefore a positive momentum. The right car has a negative velocity and therefore a negative momentum. You can sum those momenta up. The two objects will collide and stick together. They'll have a combined mass then, in this case of 7,000 kilograms, and they'll be moving in some direction with some velocity. And you can use momentum conservation to solve for that velocity in that direction. So one that kind of combines energy conservation and momentum, depending on how in detail you go, is this one we talked about in class of having a and that ball is allowed to swing down. You start out with all potential energy, you wind up with all kinetic, and you can convert between the two and learn any number of things about this scenario. What brings in momentum is when you put a block here, you can learn stuff about what's going to happen to the block after the ball comes down and hits it. So for circular motion, remember this exam will cover through circular motion and not rotational motion. They're very similar. What that means is for this exam, you don't need the moment of inertia stuff, but you do need everything that's pictured here, right? When you have an object moving in a circle with some angular velocity, you need to know how to solve for the transverse or tangential velocity. So that's the radius times the angular velocity. You need to know the definition of an angle. So how do you define that in terms of the arc length around a circle? And you need to know, how fast you're going around the circle. That is the angular velocity. How quickly that's changing. That is the angular acceleration. And you should be able to convert between radians and degrees. So a circle, circumference of a circle, if you go all the way around it, that covers 2 pi radians, which is 360 degrees. And so the conversion we use is pi radians is 180 degrees. Also for circular motion, we have the centripetal force. This is what allows something to continue going in a circle. And because F equals ma, that has an associated centripetal acceleration. And then for circular motion, because planetary motion is a very common type of circular motion, you need to know the gravitational force as well. So as an example, a great sort of circular motion problem is the following. This is one to study. So you have an object that you're swinging in a circle. So this object has some mass, and the axis of rotation is parallel to the ground. So up, down is this way. And for instance, you might want to solve different things about this. So if you're trying to ask yourself what's the minimum speed you can, or when you're swinging this thing as slow as possible, what's the tension in the string, you should be able to solve for that. The key with this type of circular motion is, remember, the centripetal force, this is just comprised of other forces that are in the system, ones that we know about. So in this case, you only have tension and gravity, and you can use these to solve for the centripetal force, and then finally go ahead and work for the tension. So then also, and this is just another example. If you have a race car executing a circle, then you should be able to figure out what the centripetal acceleration is. You may be bringing in concepts from earlier in the class. You might friction force that the car requires in order to execute that circular motion. Because in this case, friction is what is supplying all of the centripetal force that is allowing these sprint cars on a dirt track to go in the circle that they are going in. So that concludes the sort of brief overview of the things that are going to be on exam midterm 2. Again, this is going to be only a 90-minute exam, so once you start it, you have 90 minutes to complete it. And you can start it anytime from noon on April 6th until 6 p.m. on April 7th. But of course, you only have 90 minutes to complete it. So you need to start it 90 minutes before 6 p.m. on Tuesday, April 7th at the very latest. I would not recommend pushing it off until the last minute. So do study this, basically torque through circular motion. And of course, if you have any questions, feel free to email me. I do recommend creating an equation sheet, even though it's basically open note. 90 minutes is not a lot of time when it comes down to it, so you're going to want to have many of your equations handy. Okay, please do study, and good luck on the exam. Next lecture, we'll pick back up simple harmonic motion, and we'll talk about actual oscillation stuff. But remember, this and rotational motion will not be on midterm 2. That will instead be on midterm 3.